Yeah, I'd also like to thank the organizers for inviting me to this very interesting workshop. In recent years, I've been trying to think more and more about how the work I've done with climate simulation and climate change really connects up with the rest of the world. It's been very stimulating to me in terms of thinking about how I should really view my models and assess their capabilities. And so this workshop fits very neatly into that, and I appreciate the invitation. What I want to do in this presentation, my main goal is to sort of step back and try to think about the future in terms of some general principles that I'd like to draw out of my experiences at looking at climate change, especially looking at the water cycle. And along those lines, also think about what it is we know, but also what we can't know. I want to talk about some of the uncertainties that come up when we try to project the future. Uncertainties in the water cycle, which then becomes very important for thinking about how the numbers that we pull out of our models, the volumes and volumes of numbers, really can translate into what my colleagues call actionable information, usable numbers that we can actually do something with, so that we react properly to future climate change and not overreact or underreact. But before I launch into all that, then I also intend to draw some links to infectious diseases, basically echoing things that you heard in much more detail this morning from earlier speakers. Before I do that, I did graduate from Yale many years ago, and I want to give an acknowledgement to Barry Saltzman, who was a professor here for many years. Barry is the person who basically lured me into climate research. I was a physics and astronomy major here. But in many ways, Barry was the person who got me to the point of where I am today, why I'm standing here. Barry was a terrific climate researcher. He won numerous accolades throughout his career for the work he did, including receiving from the American Meteorological Society the Rossby Award, which is the highest award that it gives out for lifetime achievements back in 1998. But equally important, Barry was, as I think other people here already recognize, Barry was a very warm, wonderful human being, and that was probably also partly why I got lured into doing climate research. So many thanks to Barry for why I'm here today. To lead into what I want to talk about, before I give you an outline, I want to just sort of say what I view the global water cycle to be, drawing from this image from the U.S. Geological Survey. As you can see, it's a rather busy figure because it traces all the different ways that water flows through our climate system. The main pattern, the main cycle, you might say, is when water evaporates from the oceans, which cover most of our planet, goes into the atmosphere, condenses, and then gets transported around and gets condensed in the atmosphere, creating clouds, then falling out as liquid or solid precipitation onto the land surface as well as the ocean, and then flowing, getting stored on the land in many places, but also flowing through the land on the surface and under the surface, and then basically getting back to the ocean. With all these other little processes going on as well, which can be especially important in different regions. And in saying that, I also want to emphasize that even though I am going to be focusing on some global scale patterns and trying to draw out some general principles, that does not negate the importance of looking at regional details, as we've seen in our previous talks, and hopefully complementing what Noah presented earlier as well. Also, when water condenses, I should point out that that puts energy into the atmosphere. So this whole water cycle is important not only for the movement of water itself, where it accumulates or where it disperses, but it's also important for providing energy for the circulation of the atmosphere. It is, in fact, the single most important source of energy for atmospheric circulation. And that becomes important to think about as well when we start to think about climate change. So, why is the global water cycle important? Why is this global perspective important? And that leads into the basic outline of what I want to present today. I'll briefly talk about some prominent water cycle and health links, although I think we've seen quite a bit about that already this morning. Then I want to talk about this important point that the water cycle is expected to intensify in various ways in the future. How do we simulate that possible future climate? I want to give you a little bit of a primer on how we do global climate simulations because it brings out some of the important issues about what we can know and what we can't know. Then what are some of the features of projected changes in water processes? And again, thinking about how well do we know those changes? And then finally, a few final thoughts on implications for human health, especially infectious diseases. So The water cycle has very important roles in human health vulnerabilities. We've already seen quite a bit this morning. Obviously, it plays a role in determining where and when infectious diseases occur. There are other ways that the water cycle affects our environment that one way or another affects human health, affects our vulnerability to disease, and also affects the infrastructures that help try to keep us healthy in spite of that vulnerability. So the lack of water, as Noah pointed out, can be closely tied in with heat waves, especially the lack of precipitation. Obviously, thinking about the opposite end of the spectrum, we can get lots of water falling in places through storms. Again, those storms would be powered in part by the condensation of water into the atmosphere, but also leading to flood, accumulation of water in places, and again, leading to the breeding of disease vectors. And again, of course, the lack of water leads to drought, which causes some of its own problems, including infectious diseases. And it can, in turn, affect air and water quality. I'm listing all of these in part because we also need to think about compound effects. There was implications of that in talks we had earlier today, but it's also important to keep in mind when we start thinking about climate change that we need to be thinking about a number of different variables. I forget who raised the question, but there's a question about how well do we assess humidity simulations in these models, and we do to some extent, but clearly most of the discussion is usually talking about temperature and precipitation changes, but there really are many, many other factors that come into play, and when you start to think about all these different sources of human vulnerability and human health vulnerability, it becomes important to think about all those other factors that come into play, different measures of the climate system, and also how they vary with time. I want to present this picture of recent water stress. This is from the IPCC Fourth Assessment Report. So this is 2007. What it's showing is this issue of water stress. It's computed by basically estimating how much water is used for various purposes in different parts of the world, and then dividing it by how much water becomes replenished every year, what the annual water availability is. And you get this ratio that gives you this color scale here. And you can see that there are numerous places around the world, and they're not necessarily confined just to developing countries. In fact, oftentimes it's more developed regions that are areas that are estimated to be experiencing water stress. And some places do not experience water stress, largely because there is little population there, so there's little demand for the water. But this water stress becomes an important factor for thinking about how and when we're vulnerable to changes in the water cycle. And I want to emphasize, you may be able to read these little boxes here, but I want to emphasize a couple of them, three of them, for a couple of different reasons. 2007 report talked about multi-year drought in the US and Canada. We're experiencing substantial drought in the central part of the country even now, so this is something that comes up repeatedly, and future projections are suggesting that it's going to occur even more frequently. Damage to riparian ecosystems due to flood protection along the Elbe River. Even though we try to put controls into place, it actually can lead to other problems. And same thing with damage to aquatic ecosystems from decreased stream flow and increased salinity in the Murray-Darling Basin. This is coming about in large measure because of increased agriculture in that basin, which has changed the local water cycle substantially. And I'm pointing out these last two factors here to emphasize the point that changes in the water cycle can have impacts that are not simply poorly developed areas or areas with low infrastructure. They can have substantial impact even in our well-developed areas. And in fact, a lot of our development in many ways may actually contribute to our vulnerability to changes in the water cycle. Okay, how do we simulate possible future climate? Well, our primary tool are these global climate models. And I'm putting this picture up to emphasize one aspect of how we have uncertainty in our projections. To simulate the global climate, we need to break the planet up into little boxes or grid cells in which we solve a coupled set of equations in multiple grid boxes. In fact, there's, generally speaking, if we look at not only the grid boxes that are populating the surface here, but all the little grid cells that populate the atmospheric columns and also the ocean columns, we're usually talking about over 1 million grid cells in a typical global climate model, and several equations that are all tightly linked together, which makes for a very complex numerical problem. In fact, The more technical statement would be it's a coupled set of differential equations based on fundamental conservation laws. If you understand that, that's fine, but it's not really critical. The main point is that there are lots of equations that we're trying to solve. But in doing that, we cannot have things in as fine a detail as we always might like. Noah touched upon this earlier in his talk, talking about how we need finer resolution in some places. And looking at this diagram here, I'll point out this shaded area here. This is outlining what the continent of Australia looks like in this typical grid representation. So you can start to see and get some feel for why there are approximations involved in how we represent climate when we do these global climate simulations. And that becomes one of the first ways that we start to encounter some degree of model error or uncertainty in our projections, but only one of the ways. There's also a lot of complexity in the processes we include in these models. And this is just a very brief, sort of a cartoonish diagram of what we see in these models. And they've gotten more and more complex as years have gone by, as people have tried to put more and more processes in, try to get as close as possible to the overall Earth system. So there's lots of issues that are processes that are represented, of course, clouds, water condensing, but also circulation in the ocean and the atmosphere is implied by these arrows. In more recent times, people have started to include all sorts of chemistry in the models, not only the ozone chemistry in the stratosphere, but also chemistry down where we live, looking at effluents from different types of industrial processes, and also making vegetation more and more like the real world, not only having it respond to the whole annual cycle of sunlight and precipitation, but also to actually grow and decay and actually start to move about within the climate models. And in addition to that, becoming more and more detailed, there's no title for it here, but more and more detailed with how we simulate how water moves through the climate system. So these have become more and more complex. That complexity actually makes it even more difficult to interpret the models in many respects and to understand what's going on. But then we're trying to understand the real world, which is equally, if not more so, complex. So we need these models. So there are different limits that start to occur in our ability to understand what the future actually holds. These limits come about because of the complexity of the problem and our ability to represent it well or not so well, and then limits on the knowledge of that complexity and the computing power that we have to work with. One reason why we have the number of grid boxes we have, and not many, many more, of course, is the limitations on our computers. We could put in lots and lots more grid boxes. We could have very fine scale resolution, and we probably would then be able to simulate the climate for a year using about 10 years of our time. Obviously, that's not a realistic way to proceed. So all of these lead to different sources of uncertainty. As I already talked about, the grid spacing is one of them. There are limits to just how finely we can resolve different processes. There's also our important knowledge shortcomings. What should we be including in these models? What is perhaps nice to include but not necessary? And even with what we include, how well do we understand the processes we include? A lot of things that are included, especially the whole business of trying to simulate water condensation, cloud formation, precipitation is still, in many respects, only rudimentarily understood. There's lots more we need to understand about how to represent these processes well. So these all become uncertainties. And there's also the whole question of what people call structural uncertainty, which is what are the unknown unknowns that we haven't even thought about including? Is there something out there lurking that's actually very important and we just have not learned enough about the climate system to include it yet? What are the surprises that are awaiting us? And then going back to those complicated equations, the nonlinear mathematics, which in some ways are emulating what goes on in the real world, they bring into play another kind of uncertainty, which is just the fact that in any complex system, there is a certain degree of unpredictability that is always going to be there that comes about from the complex nature of all the interactions that go on in that system. There's a part that's always going to be unpredictable, and we have to recognize that as well. And then, of course, finally, humans. All I've talked about so far are just basic physical, chemical, biological processes. In many respects, I'm always glad that I'm just a physical climate scientist, because when I start to think about what humans might do, I just start to get totally lost. And that's And yet that's a very important part of thinking about the future, because we have to understand how humans are going to respond to changing climate, what types of controls we may or may not put in place. Okay, what are the features of projected changes in the water processes? How well do we know them? This diagram here, you saw something like this earlier from NOAA. This is actually using more recent global climate models, the so-called CMIP-5 models. This is the change in global surface temperature projected going back over the historical period and then projecting on well into the future. The reason why I'm showing you this here is I don't want to always dwell on global temperature, because even though it's a driver and gives a lot of information about what to expect, it, of course, is global. It's a global average. But the main reason why I'm showing you this is this little box here that says future scenarios. This gets back at the human component of all of this. These things called RCP 2.6, 4.5, 6.0, 8.5, those are all different scenarios that people have put together trying to estimate how humans might respond to potential for climate change and how they might put in regulations or no regulations to curb the growth of greenhouse gases in the atmosphere and in the oceans. So there are different degrees of control that are in place. This RCP 2.6 assumes that humans are really going to get together on a global scale and enact global regulations and really work very strenuously to put in alternative sources of energy while not constraining development overly, to arrive at a situation where the emissions actually start to go down, and in fact, even the greenhouse gas levels in the atmosphere start to go down, giving you this leveling off of temperature increase. Now, I should point out that the scale here is relative to the year 2000, so it doesn't include the increase also from the pre-industrial period. If you're thinking about that 2-degree threshold that people have been talking about as a sort of responsible limit for how much warming we can allow, you have to add about 0.6 degrees to this scale here. So really something round about here would correspond to that 2-degree limit. And this is the only scenario that keeps us below that 2-degree threshold. These other scenarios involve varying degrees of control or lack of control going up to this RCP 8.5, which in some sense mimics what people have talked about in the past as being a business as usual scenario, where everybody just goes their own way, everybody just develops their own resources, their own energy supplies as they see fit for their own nation or own region, and there are essentially no controls on the emissions. In recent years, we've actually been following something, the globe has been following something akin to this RCP 8.5 scenario, although I saw a figure just recently that showed that the United States, for various reasons, has actually had its emissions start to decrease, partly because of controls, but partly because of economic reasons and other factors. So if we were to take what's happened in recent years, we might say we're on this pathway, but you can also see that as you go through this diagram that all these scenarios don't really start to diverge substantially until about mid-century. So to some extent, what that tells us is that we're on a track to have some degree of warming no matter what we do in a reasonable way for the next 40 to 50 years or so. And then after that, what we do, and that includes issues that we start to confront now, start to have an impact down the road in terms of what pathway the Earth follows as a whole, which means what we do now affects what our children, grandchildren, and their children will start to experience. Even if we were able to just stop emissions completely right now, that type of simulation has not been done with this set of models, we would still get some warming that occurs. But that would obviously be so draconian and unrealistic. So these are all attempting to be fairly realistic scenarios about what humans might do. But you can also see that there's a spread in what the response would be. You also see there's shading about each of these curves. That shading represents the spread that you get from all the different models, and these are the numbers of models, that simulated those different scenarios. So all those other uncertainties start to come into play, including that unpredictability that's part of the climate system. This gives us some measure of the uncertainty, but usually people understand that this is probably an underestimate of the overall uncertainty, because there are other factors lurking out there that we may not recognize yet as being important. So human factors become very important when we think about the future, especially as we go deep into this century. And we can also see some evidence in this diagram as well of what it means to have all those other uncertainties come into play. Some of that uncertainty is never going to go away, including some of the uncertainty about what humans are going to do. Okay, what do we see in terms of some general principles that start to emerge when we look at the globe as a whole, and in particular start to look at regional patterns? It's generally recognized for reasons I don't have time to go into here, that the global average change in precipitation is going to involve an increase in the global precipitation at a rate of about 1 to 3% per degree Celsius increase. And what I've got plotted here is the change in precipitation at the end of the 21st century relative to this baseline period that was established for a reference point. There are important regional differences, and to understand those regional differences, I want to explain a little bit about what's meant by this hatching and these dotted or stippled areas here. The stippled areas here are an estimate of places where we think we have a fairly good confidence of the type of change that will occur and maybe even the magnitude of the change. These are places where the models generally agree on the sign of the change, show a fair amount of agreement on the magnitude of the change, and that change is generally much larger than that unpredictable part of the climate system, a term that people often, that unpredictable part is oftentimes called natural variability. So something that is a substantial change relative to any natural fluctuations that might occur. And that leads to the stippled areas here on these diagrams. And the hatched areas here are places where there is much, much less confidence about what the change might be. This can come about because the change is actually projected to be very small. So you might expect that relative to the noise of that variability, there's no confidence. But it can also be that the models just show very different results in what they project that change to be. They may even disagree on the sign of the change. So those are places where we do not have confidence in the magnitude of the change. The scale down here is in percent, showing you that the degree of increase or decrease that is projected to occur by taking that ensemble of models together to produce these figures. This is for the season December, January, February. 35 models contributed to it. June, July, and August, also 35 models contributed to it. Okay, some general principles that you can extract from all of this. Generally speaking, we see in this generation of models and also in earlier generation of models that there are increases in precipitation in the high latitudes, especially in the winter season. This occurs because the greatest amount of warming is projected to occur, especially in the northern high latitudes. Warmer air can have more moisture present, so if there's more moisture present, then you can have more falling out as precipitation. So in these high latitude areas, in both polar regions, but especially in the Arctic, the key driver is the fact that you have warming, which then can allow more precipitation to occur. It's sort of a contrast in the process behavior in the low latitudes. Generally speaking, where you have more precipitation, you have less warming because that greater precipitation leaves more water on the ground. There's more water that can evaporate. As you would have recognized, whenever you step out of a swimming pool and water is evaporating off your skin, it cools you off. That cooling effect comes into play on a large scale in our climate system. And in contrast, where there's less precipitation occurring, that leads to drying. And as Noah talked about earlier, that can promote more warming. You have less of that evaporative cooling. Also, of course, we have more precipitation. You tend to have more cloud cover. That's going to block the sunlight from heating the surface. So in the low latitudes, changes in the water cycle to a first approximation are driving, or at least playing an important role in the temperature changes rather than the temperature changes driving the changes in high latitudes. A rough general principle as a starting point is to recognize that there's going to be a tendency for areas that are already dry to get drier, areas that are already wet to get wetter. It's not a perfect principle, but it's a good starting point to think about for any region in the world. If you want to start again getting down to the very detailed regional behavior, you of course do have to think about local circulations and local responses. But to get a general picture, this is a useful principle to keep in mind. Another principle to keep in mind pertains to humidity levels in the atmosphere, which we've already heard can be very important. This shows the change in atmospheric relative humidity. Again, same changes, changes relative to the same baseline. These are all using that RCP 8.5 scenario. I should have pointed that out on the previous slide as well. So these are showing, in essence, the maximum changes that you might get, or the most confident changes. Again, wintertime, northern weather time, December, January, February, June, July, and August, and then the annual average. I could have probably just put up just one of these figures and given you the same result, but I did it just to show you that it's a very consistent behavior, both for mid-century here, 2046 to 2065, and also at the end of the century. What you see, especially over land, very little stippling, lots of hatching over land areas, lots of stippling over the oceans, but that's because they have lots of water available. But the main point here is that over land areas, very little stippling and fair amount of hatching, stippling showing up generally in some dry areas. The main points I want to make here is that there's much uncertainty in the change, especially over land, where you see lots of hatched areas, and also very little change. The scale here is only an increase or decrease of minus 10 to plus 10 percentage points. So a general principle that emerges, and we've known about this from observations as well, and also from earlier generations of models, is that relative humidity tends to stay fairly constant. That leads to a point that Noah made earlier, that humidity will tend to go up about 7%. Absolute humidity, or specific humidity, will tend to go up about 7% per degree Celsius warming. So absolute humidity can increase very rapidly. That means we can start to put more and more moisture into the atmosphere. And the reason why we see lots of stippling over the oceans is because the oceans are persistent, available source of water. So if the atmosphere can start to take up more, the oceans are going to readily supply it. But over land, very little change. This is a very important constraint on the behavior of the water cycle. Soil moisture is one way of, the models do not always have those nice hydrological models like we saw discussed in Jeffrey's talk before mine. It'd be nice if they did, but we can have other proxies for it. One of them is that the models do try to represent soil moisture. What you see here is that the scale here is drying, and the red, darker shades, wetting, and the bluer shades. What you see is, again, large areas of hatching over land, except for areas where there's drying. The soil moisture becomes an indicator of where water might or might not be accumulating on the land surface, which obviously has disease implications. Areas of significant drying are areas where there's reduced precipitation, and those are the only areas that really show up with lots of stippling. So a fair amount of confidence that there's going to be drying in many parts of the planet. No areas of significant increase in soil moisture, even in the far north where there was substantial and significant increases in precipitation. The soil moisture itself is not changing very much. That's occurring in part because not only does precipitation increase, but as it gets warmer, you have stronger evaporation and stronger transpiration from plants. So a lot of that moisture just goes right back into the atmosphere, or it goes into runoff. Runoff is the model's way of representing what flows in rivers, even though a lot of these models do not have rivers themselves. Again, changes from the same baseline period to the end of the century. This is the annual average, 28 models. So now you see significant changes in the runoff in high latitude. So a lot of that water is going into the rivers, possibly accumulating in places, possibly increasing flooding, possibly leading to new water bodies that could be breeding grounds for various types of mosquitoes and other insects. Otherwise, fair amount of hatching and clearly some significant decrease in runoff where you have drying. So areas of significant drying are areas of where there's reduced precipitation, reduced flow of water into rivers. And again, note the degree of confidence we have in going from region to region here. Some places we're more confident about some of these changes than others. And as Jeffrey showed in his talk, it's very important to think about all these different aspects of the water cycle that I showed you, not simply just precipitation when you want to start thinking about the disease implications. Okay, finally, just some implications of all this for human health, which really, again, is echoing a lot of what we heard earlier today. Focusing just here on Africa, this is from the IPCC Fourth Assessment Report as well. Places where there's high mortality risk due to water factors. And there are water factors involving drought increasing in some places, water factors involving what they say hydro only, meaning changes in precipitation and the whole more intensification of the water cycle. But equally important, these compound factors of where you can have drought and changes as well as hydrological changes, basically a lot of increase in drought, but also increases in precipitation. What seems somewhat contradictory sometimes is you can have in any given location, you can have an increase in drought because precipitation may occur less and less frequently, but at the same time, when precipitation does occur, it may occur much more in large downbursts that can cause flooding. And that can happen simply because you have more water vapor present in the atmosphere in that warmer climate. So you can have increased flooding and increased drought both going on in the same place, which then has lots of implications for how we think about infectious diseases going into the future. And that can lead to complex and serial disasters. We already saw, actually, thank you, Jeffrey, in your talk, talking about how it's important to have periods of dryness followed by periods of wetting to promote certain disease vectors. Well, that can occur in other complex ways or in serial ways of different events following each other. And that can amplify the vulnerability to all sorts of human health problems. Again, drawing from the IPCC Fourth Assessment Report, changes that were places where there are expected to be high-risk zones for malaria changes. You actually saw this figure earlier. And also changes due to epidemic meningitis. With malaria, again, other people have talked about this in much better detail than myself. Even though there's endemic malaria in this white area in the middle, it's when it starts to spread to other locations that you encounter vulnerable populations who maybe aren't quite so hardened against it or haven't taken all the appropriate measures to protect against it. The interesting thing about meningitis showing up here is it's due to a reduction in the intensity of the water cycle, increased dryness, low humidity, and dusty conditions. So again, re-emphasizing that point that we have problems when we have too much water, but also problems when water amounts go down that can lead to development of meningitis. So finally, and I'm also showing this last figure here, this is also from the IPCC Fourth Assessment Report. This was their estimate of degrees of confidence in terms of how climate change can affect human health. And what I'm putting this up here for is to bring out the fact that most of these are related to issues involving water. The contraction and expansion of malaria zones are related, of course, to temperature, but also to issues of humidity, precipitation, and drought. Possibly there could be places where malaria contracts, so beneficial effects of climate change, but they drew a slightly larger arrow indicating that probably overall it's going to be a negative consequence. Changes, increased malnutrition, increases the number of people suffering diseases and deaths and injuries from extreme weather events, probably tied into changes in droughts and floods, as well as pests that can carry diseases. As a side note, it was interesting that no one mentioned corn before, because having lived in the Midwest for 20 years now, I very much appreciate what corn means, and also how corn pathogens get transmitted. One side effect of global warming is that pests that used to get killed off in the wintertime and could winter over only very far south of Iowa and therefore needed all summer before they could even get up to Iowa, now can winter over much closer to Iowa. So we're seeing diseases for corn that are starting to spread into our region much more readily. Okay, increased frequency of cardiorespiratory diseases. Again, meningitis, drought can promote dusty air. So you may get flooding in a region, but you may also get drought promoting dusty air, and any cardiorespiratory disease can be affected that way. Changes in the range of infectious disease vectors. We've already seen lots of information about this. Obviously, it's related to temperature, but also changes in the water cycle. And finally, burden of diarrheal diseases, all related to water quality influenced by stagnation. And again, places where you have increased heavy downpours, you're more likely to have flooding, accumulation of water that can lead to diseases. So to summarize, despite the various uncertainties that I talked about, there are some things that we have confidence about looking towards the future. There's generally going to be a tendency for wet areas to get wetter, drier areas to get drier. Again, don't view this as being a hard and fast principle. It depends on specific locations and how the circulation changes. But if you want to start thinking globally or in broad scale about infectious diseases, this is a starting point for thinking about how things will change. And as I pointed out, some places may experience both changes, more intense rain events and more drought. Water changes of all kinds, as I've also pointed out, and as our previous talks have pointed out, have important implications for disease transmission And as I also emphasized, no one is immune from the impacts of water cycle changes, and therefore these water cycle changes can affect all of us no matter where we are. Thank you for your time.